Right, okay, so this is a work that we presented at KCAP in 2019, before the pandemic, the good old times. Okay, so, well, I don't think I need to describe to you what is planning, but the important thing here is that in domain-independent planning, we have a logical separation between the planning engine, so the reasoning side, the automated side, and the knowledge models, so the domain and the problem model. In the domain models, we have operators, properties of the environment, the usual thing. In the problem model, we have a description of a specific problem that we want to be solved right now. And the way in which we have been working as a community is that planning engines, despite the fact that they are more and more used in real-world applications, are designed and tested on what we can probably call good quality models. So models which has been polished and designed from experts that know what we are doing, usually. And one of the aims of this work is basically to investigate the robustness of domain-independent planning to issues in the input knowledge models, and to raise awareness about the impact, the potential impact of maliciously modified knowledge. And the perspective we are taking here, that I think is quite useful for this kind of analysis, is an attacker's perspective. So we are putting ourselves in the shoes of an hypothetical attacker that can manipulate the input of planning engines for reducing planning capacity of someone that can be a competitor, an adversary, anything like that. And our standing point that I believe, well, we decided it, but I believe makes a lot of sense, is that attacks should and cannot be detected by a post-hoc analysis of the generated solution plans. So you want to make changes that are basically impossible to spot unless you find exactly where the models has been modified. So by looking at plans, you cannot spot that an attack has been performed. And this is because, or as we all know, if there are issues in the knowledge models, they need a very expensive and time-consuming analysis in order to be identified. That is particularly true for applications where you have large models that are used, or where models are created in real time, maybe by putting together information from different sensors and different data. And in the context of this work, we introduce a formal notion of plan equivalence, so the fact that models can create the same set of plans, or plan dominance, where one model can create a set of plans which is a superset of another one. And in order to identify the impact of this modified knowledge, we consider, and we formally defined, 3 classes of modifications that can satisfy the notion of plan equivalence. So they can satisfy the fact that you can create the same plan so that you cannot spot changes by post-hoc analysis, which are increasing the number of objects, applying or generating inapplicable dummy operators, or dead-end dummy operators. And increasing the number of objects, that's probably the easiest way to modify models, so by adding objects to the problems. The big question here is how to make sure that those objects, those fictionary objects that we are adding, are not appearing in solution. And there are a number of ways which you can guarantee that. Objects must not appear in the initial state. Objects must not be mentioned in the goal state, of course. And these are quite trivial reasons. And there must be no operator that allows to make true an object if that object is not mentioned in preconditions. So you shouldn't have an operator like the one that I'm showing on this slide. If these preconditions are met, then it is true to say that adding new objects to the problem will not show them in any valid solution plan. And inapplicable dummy operators are similar. So what we want to do is to apply or to add to models operators that can never be applied. A potential example is to drop an object you are carrying. The object has to be already dropped. That is a mistake that we have all made when playing with a gripper domain, for instance. And this is a kind of an example. So, well, you don't need actually any specific condition to know that these kind of operators will never be shown in plans, but the fact that they are inapplicable and completely useless. And then we have dead-end dummy operators. So basically operators which are leading to a dead end. So you are sure that the goal cannot be reached if that operator is applied. So it comes without saying that any valid plan cannot have this operator in there unless the goal is the dead end state, which is quite unusual, I would say. An example here is when you drop an object that you are carrying, the object completely disappears. And that can be its representation in terms of PDDL. I'm not going into the details of PDDL here. I think that these are quite straightforward examples that you can understand. So how did we set up things in to test the impact of these three cases on the performance of planning engines? So we selected 5 planning engines, and we used 5 domain models that we took from international planning competitions. We took them from IPCs because they are believed to be of good quality, and so we are starting from a baseline which is safe and good. And we selected some of them that satisfy our conditions, so where you can add unusable objects, dummy operators, and dead ends without them being spotted in the solutions. What we did was then randomly generate 20 instances per domain, and the generated plans generated after the modifications had been implemented in the models were validated using val against the original models to make sure that generated plans are actually valid for the original one. And okay, experimental setting was run, all the experiments were run on a dedicated machine, 5 minutes CPU time seconds, as in the agile track of the IPC, 4 GB per execution. And let's now go through the results, actually. So first of all, increasing the objects. Ideally, there should be no fact increase. So it should be quite easy for any planning engine to identify that these objects are completely useless, and so not to show any sort of increase in terms of the predicates that need to be considered throughout the planning search. And we can see that in general, in about a quarter of the cases, planners are still not able to effectively prune these dummy objects. And this is having a not huge, but noticeable impact on runtime for most of the planners. Probe seems to be the most robust on these regards, but also Madagascar, in some cases, works pretty well. In some others, it's having a strong impact on the runtime, besides the fact that these additional facts are pruned. For some planners like BFWC, adding unusual objects can have a positive impact on the performance, and that's probably due to some internal behavior of the system. And in general, increasing objects has a very limited effect, but despite that, some planners are still not able to prune them completely out. When it comes to inapplicable dummy operators, or operators that you can never apply and that are completely useless, most of the benchmarks for the considered planning engines, so the planning engines are very robust when it comes to this sort of attack. I think Chrpa, which we are presenting here, is the only model in which you can see some noticeable changes in terms of coverage, actions, and the time needed. So here you can see the delta coverage with regard to the original domain model, the increase in terms of multiplier of a number of actions which are considered throughout the planning process, and how the time is increased. Between brackets, you have the original time for solving the original planning problem, and then you have a multiplier that results after the application of the changes. And the final kind of modification that we consider was dead-end dummy operator, and these are very negatively affecting the performance of planners. And we can see here the two extremes, Chrpa and floor tile, where you can see again how the number of actions is increased and how the runtimes are increased and coverage is affected. That seems to be, these have a very strong impact. And planning is being more and more, why did we run these sort of experiments? Because planning is being more and more used in applications, and this is raising questions about the robustness of planning techniques. To raise awareness around robustness and to about the possibilities of malicious attacks, what we did was formally define 3 classes of attacks, formally define what is hard to spot and fix as a kind of attack, and demonstrate that state-of-the-art planning techniques, at least from 2019, can be quite sensitive to some, at least, of the attacks that we design. What we'd like the community now to start doing is investigate techniques and approaches to improve the robustness of planners. That can be a more in-depth reprocessing or additional tools for supporting non-experts which are dealing with planners and planning engines. Because it's worth remarking that many of the issues that we categorize here as potential attacks are actually can be actually the result of accidental complexity. So it can just be the result of someone not using planning tools in the proper way. And that's all. I'm happy to answer questions.